Good morning. Today we are going to be talking about orbital notation and some of the rules that govern orbital notation as well as electron configuration. So I need you to write down these notes in your notebook about some of the principles and the rules. There's 3 of them that dictate how electron configuration works. So the first one is called off-ball principle. And the off-ball principle says that the lowest energy orbital available must be filled first. So for example, this is why we fill it in this way: 1s2, 2s2, 2p6, 3s2, okay? Because that means that our s orbitals are filled first, so they are lower in energy than our p orbitals. That's why you fill the 2s before you fill the 2p. Similarly, if we keep going, 3p6, 4s2, 3d10, that is why your 4s comes before the 3d, because it is slightly lower in energy, even though it is the valence, because 4 is a little bit further out than 3d. Energy-wise, your 3d has a little bit more energy, okay? So that is what off-ball principle says. So that is why you can't do this out of order. Okay, next slide. The Pauli exclusion principle says that no 2 electrons can have the same 4 quantum numbers. So that is why when we talked about the spin of electrons, that is what makes the electrons in the same orbital have a different set of quantum numbers. They have to have opposite spins. So the way that we represent this when we are doing orbital notation is we use arrows that are pointing in opposite directions. So for example, this is an example of orbital notation, which we'll get into a little bit later, that uses lines that represent each of the orbitals. And that is why, for example, in this s orbital, 1s, you have the electrons or the arrows in opposite directions, showing that they have opposite spins. Same thing in the 2s here, they have opposite spins because they're in the same orbital on the same line. In this case, this is violating the Pauli exclusion principle because they are going in the same direction, which means they would have the same spin, which is not allowed. Okay, and the final rule is called Hund's rule. Hund's rule states that you have to put 1 electron in each orbital of equal energy before you can pair them. So this really applies to orbitals that have more than 1 in the energy level. So we're talking about p, d, and f. So for example, the 2p, we can have 3 orbitals for p. You can have 1 for s, you can have 3 for p, 5 for d, and 7 for f. And this determines how many lines you write, because 1 line equals 1 orbital. 3 lines equals 3 orbitals. 5 lines equals 5 orbitals, and 7 lines will equal 7 orbitals. So that is why here you have 3 lines for the 2p2. So Hund's rule says that you cannot pair them in the same line until you put 1 in each. And you can kind of think of this like sharing rooms. So if you have 3 rooms available, it is probably better, especially if you're brothers and sisters, to have 1 person in each room before you start pairing them. This would not be ideal. Okay, so this violates Hund's rule because you have 2 electrons in the same space and you've got 2 that are empty. So you have to fill them all up first with 1 before you can go back and pair them. Now we're going to look at orbital notation and how we determine the orbital notation for different elements on the periodic table. So orbital notation is a little bit more specific way to determine exactly where electrons are, and it also shows the spin. So just like I mentioned on the last slide, s orbitals only will have 1 line, p orbitals will always have 3 lines, d orbitals will have 5 lines, and f orbitals have 7 lines. If you would like to watch somebody else do a video for orbital diagrams, it is linked here. So if you go back to the original slideshow, you can click on the orbital diagram video and it will give you some more examples. Okay, so now I want to go to the next slide. Maybe. Here we go. There we go. Okay, so now this shows the orbital notation for nitrogen. What I suggest you do when you're doing orbital notation is go ahead and do the original electron configuration first. So for nitrogen, we have 1s2, 2s2, 2p3. Then once you have your original configuration, you're going to go through and you're going to draw boxes or draw lines. I usually do lines, but some people show boxes. You're going to label them. So for S, I always have just one line or one box, and then I label it 1s. The electrons that are in there come from your superscript number. And we know, according to the Pauli exclusion principle, that if you put them on the same line, the arrows have to be in opposite directions. Okay, so I have two arrows here because it tells me two electrons, and they have to be in opposite directions according to Pauli exclusion principle. So then I've done that one. Then I go to the next one. It's an S, so it also is one line or one box. And I have two electrons in there. They have to be opposite spins, one up, one down, and I label it 2s. When I get to a p orbital, I automatically draw 3 lines because there's 3 different p orbitals. In this case, I only have 3 electrons, which means that, according to Hund's rule, I have to put 1 in each. I can't pair them, okay? Now, when you put 1 in each, it doesn't matter if you put them all up or if you put them all down, but they do all have to be spinning the same direction. So I can't have 1 up, 1 down, 1 up, or 1 down, 1 up, 1 down. They all have to be going the same way before I pair them, okay? So let's do another example, and I'm going to switch over to the periodic table now, and we'll do another example of orbital notation. Okay, so here's my periodic table. Now let's do an example of, let's do something like manganese. We'll do Mn. Okay, so manganese is right here. So I would do my entire configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5. Okay, so when I do this, for every S, I draw a line. And I like to label it because then that way I don't get confused about where I am. And then 2 arrows, so 1 up, 1 down. Then I go to the next one. Now, technically, if I was doing this correctly, it takes a lot of paper, but my 1s is the lowest energy, so my 2s should be a little bit higher. 1 up, 1 down. And then my 2p should be a little bit higher, but this time I have 3 lines because it's 2p. And then I would do 1 up, 1 up, 1 up, 1 down, 1 down, 1 down. I think it's way easier if you practice using Hund's rule every time by putting 1 in each and then pairing them. You'll be less likely to forget it if you practice doing it that way. Now, I'm running out of room, so I'm not going to keep going up, but you get the idea. You can go up a little bit each time to show that they have slightly increasing energy. Some people don't do that, and they just assume that you know that. So I'm going to move down here for 3s. 1 up, 1 down. 3p, 1, 2, 3. 1 up, 1 up, 1 up, 1 down, 1 down, 1 down, since I have 6. Then my 4s, 1 up, 1 down. And now when you get to 3d, I'm going to move way up here, which normally you would not do. You would keep them all in a line. But I'm running out of room. So when you do 3d, remember D has 5 lines. 1, 2, 3, 4, 5. In this case, I'm going to put 1 in each line. Now, I want you to note that even if we were doing chromium and it was 3d4, I would still draw 5 lines. You're still going to draw all of the lines that are available, even if one of them does not have an electron in it. Same thing for P. You're going to draw all 3 lines, even if there's one that doesn't have an electron. Okay, so these all are going to go up in this case, and then that would be my total orbital notation for manganese.